Thanks, Oriana, for the nice introduction. Thank all of you for being here tonight. It's really a pleasure for me to have the opportunity to really talk about what I do in another way, right? And this is an important part about science. It's not just about doing it, it's about communicating it in a way which is accessible to everyone, right? That's a big part of what I believe in. So the topic of my talk is capturing atomic motion with the world's fastest cameras. So really what I'm going to hope to convey to you today is really the core physics that's kind of needed to understand how these cameras work, and also, you know, what kind of physics do you then use them to look at. These are two very different things, but they really go hand in hand when you really investigate this whole thing. So it's going to be kind of a journey, right? It's going to be a journey through technology, and what you'll realize, hopefully, if I've done a good job, is that, you know, things just get better and better, right? You invent something and you combine that with another invention, and then you have another invention, and this is now useful for something new. So that's really a consistent theme in the field that I'm so privileged to do my work in. So just here's a quote which I particularly like, which summarizes that well. And it's by Freeman Dyson. The effect of concept-driven scientific revolution is to explain old things in new ways. This is, you know, the power of idea. The effect of tool-driven scientific revolution is to discover new things that then have to be explained, right? So there's a lot of stuff that we never knew was out there, right? And then once we found it, we say, wow, we need to find a way to talk about this. These are two sort of, I don't know, the yin and the yang, you could say, of science. So what's our starting point, right? This is not, you know, I'm sure most of you know that atoms are small, but they're also extremely fast, right? And really the challenge that motivates my research is how do you watch what they do, right? We live in a world of materials, right? We don't live in a world of single atoms. We live in a world where a lot of atoms have collected and formed solids and formed us, right? They've chosen to arrange themselves in such a way that produces different types of materials, different types of organisms, everything, right? So the big question is why, right? What is it about individual atoms such that when you put them together, you know, 10 to the 23 of them together, they preferentially form one thing over the other, right? So understanding why this occurs is really one of the central themes of what we call material science, even chemistry, right? So yeah, that's kind of, we want to catch this guy. We want to see what he's up to, not on average, but sort of at a snapshot in time. So hopefully this has not run out of batteries. Maybe it did. Suppose you want to take a picture. What do most people do, right? They whip out their smartphone, they try to do something, and then they basically click and hope for the best. And, you know, if it's good, you have a nice picture. If it's not, you take another one, you try again, right? So depending on what you're trying to take a picture of, you really have to think carefully. So usually you have an object which is illuminated, and the basic ingredients of a camera are you have a lens which focuses light, you have an aperture which lets light in, you have a shutter which basically says when a sensor is going to be exposed to light, and then you take a picture, right? But how fast can you take pictures, right? This is going to be dictated by how quickly you can expose that sensor to light. A typical camera might have a shutter speed that ranges from 1 millisecond to 10 seconds, depending on what you want to do. You can see sort of in this picture with a long exposure, a long shutter speed. The foreground, consisting of cars and fast-moving objects, are blurred. The background is nicely in focus because why? Well, because it's not moving. So this sort of illustrates the effect of different timescales when you actually want to take a picture or make a movie of something. So how this was first tackled was quite a famous experiment, I guess, which called the horse in motion. This was the first way to kind of view or make a movie, right? And it was done by the guy up in the top corner, Ian Weird Muybridge, who essentially was like a photographer aficionado for his time. And he was hired by Leland Stanford, to be founder of Stanford University, to determine if at any point in time all four legs of a horse were off the ground. This was considered like a must-know thing back in 1878. Leland Stanford had bet a lot of money to someone else that he was like, I'm pretty sure all four legs are off the ground. And the other guy was like, well, prove it. So he hired this guy to essentially set up on a horse track a bunch of cameras, each connected to a tripwire. And as the horse ran through it, it set off a bunch of different cameras and took a bunch of snapshots, as you see here. And sure enough, if you look in this frame up here, boom, you see that the horse, in fact, is completely off the ground, kind of mid-stride. Leland Stanford got his money, and he won the bragging rights and probably bought more horses and eventually founded Stanford University. What did this hold for, like, human knowledge? Well, for one thing, people were not drawing horses correctly. So here you can see people were always drawing horses in this like lunging form, right? With all four legs stretched out. It's just wrong, right? When they're stretched out like that, at least 1, maybe 2 feet are on the ground. And it's only when they're in mid-stride like this that they're completely off the ground. Revolutionary, right?
At least in California.
Pardon me?
At least in California.
Yeah, exactly, yeah. This is what they were up to. The point is, this led to what we call now the stroboscopic method, where if you want to take a picture of something moving really fast, but you have a sensor or a camera which is really slow, one way around that is to illuminate the object really quickly. And then what you get is essentially the addition of many, many different pictures. Each one has a different snapshot of the motion, as shown here in this photo of someone serving a tennis ball. So it's this concept, essentially using what we would call a pulsed illumination, a flash, to illuminate the sample that we want to start from. So the question is, can we do this for something similar in a material? Okay, so what are we dealing with? We have atoms that are usually arranged in an ordered manner, as kind of shown here in a simple lattice of balls, whatever. Now, what are the sort of time scales and distance scales that we need to be aware of? Well, we should be aware of kind of the distance between atoms. This is what people usually call 1 angstrom. That's kind of, you take a trillionth of a meter, you divide it by 10, and then that's an angstrom. Pretty small, right? Similarly for time, we think of atoms being in a solid, they're not moving. Well, actually they are. They're always kind of vibrating a bit around what is their equilibrium position. And the time it takes for them to go back and forth around this equilibrium position, just kind of oscillating due to the heat that they have, this is 1 picosecond. So this is 10 to the minus 12 of a second. So these are the basic scales of distance and time that are intrinsic to a material. And if we have any hope of seeing this, we need to find a way to take a picture that can resolve spatially this distance and resolve temporally this time scale. Otherwise, you're just going to see an average, right? And we don't want that. We want to take snapshots. Can we use light? Well, the answer is actually no. And this is kind of rooted in sort of fundamental physics principle. So you can, perhaps if you want after this talk, you can browse the internet and look at pictures of various optical microscopy pictures, and you'll basically see that as you try to look smaller and smaller, something on the order of 1 micron or less, it's not possible to focus the image any further. And this is what physicists call the diffraction limit, and it's essentially rooted in the fact that light is a wave, and so it goes up and down. And if the spatial scale of what you're trying to take a picture of is similar to the distance over which it goes up and down, that light is going to be bent, right? And that's what leads to blurriness and sort of defocusing, which you can't easily get rid of with what we would call conventional lenses. Okay, so we can't really use light. So I'll pause there for now. but at the same time, I want to introduce some important properties of light as a wave, and then apply that to waves in general. And then from there, we'll see how we can further approach this problem. So I just said light travels as a wave, so it goes up and down over some distance that we call a wavelength, has a speed of light. And essentially what can happen is, here's sort of a picture of what I was just describing verbally. If light is incident on some small structure, illustrated here by just a gap, which is similar to the size of its wavelength, as it propagates through that gap, it's going to be bent by the presence of that gap, sort of leading to these curved wave fronts here. This effect is called diffraction. Whereas if it propagates by objects which are relatively much bigger than the wavelength, essentially nothing is going to happen. What you need to know from this is this light, that we call a plane wave, can be focused easily and therefore imaged easily. This other light, which is diffracted, it's more complicated. It complicates things. So what we want to do is actually, is there a way to actually make use of this somehow, this diffraction effect? One other thing I'd like to, which is related, that I'll tell you about light, is that light waves can interfere with each other. Illustrated here on the right, you have an orange curve and a green curve, and basically if you add them together, you get nothing. So this is what we would call perfectly destructive interference. Those two light waves essentially cancel each other out. Similarly, you could imagine adding a combination of random waves. You get something like this. So that's interference. Waves add. This is generally true of all waves. Waves in the ocean, gravitational waves, anything. Let's go back to diffraction for a second, keeping in mind this property of interference. Suppose I have my wave, which is incident upon some structure, which is periodic. This is actually where I do my demo. Good thing I remembered. So what I'm going to show you now is, so I have a small laser here, totally safe, don't worry. This laser produces red light, and I'm just going to remove some things. This laser produces red light. As you can see there, right? Can everybody see? Nobody's colorblind. What I'm going to do now is put in front of this light what, as a physicist, we would call a diffraction grating. Essentially, this is glass. There's a bunch of lines on this glass. In between the lines, the light goes through, but on the lines, it gets blocked. Basically, this array of slits that's kind of illustrated here. I'm going to slide that in front, and can people kind of see this? Is this roughly visible? So now there are more dots. Okay, what's happening? So this array of lines that I told you on this diffraction grating produces something like this, right? Essentially, the waves will emanate between those lines in what we would call, circular or spherical waves, and farther away, there will be regions in space where those waves have interfered destructively or constructively with each other. So, and that's exactly kind of what you see here. So I've placed like my screen back here, and I can see the interference pattern produces basically a strip of laser spots. And if it was perfectly dark in here with a more powerful laser, it would keep going, right? I can put another one in the other direction where it's hard to see now, but I've just essentially put another row of lines in the other direction, and now each one of those beams which gets diffracted interferes again and produces just an array of spots, right? So another one of these but in the dimension out of the plane. So this is an interference pattern produced by the light as a result of propagating through some structure which has some order to it. So there's just an arrangement of lines. And the structure of that produces an interference pattern which essentially transforms these lines in a way which can then be seen, as you see right there. All right, so that's kind of interesting. We found a way to use this diffraction interference concept and actually produce something which is a real image, right? We all agree that those spots over there are interesting, but it's not exactly the real thing, right? This isn't like an image of those lines. It's an interference pattern produced by those lines. Nonetheless, it still has some very useful information. I'm going to switch gears a little bit. We're still going to remain on the topic of interference, but I have to talk about, now I have to deal with the issue of time. So the ultrashort laser pulse. This is something that we need, just pretty much inevitably, right? If we want to make a strobe light to take pictures, and we need to make a strobe light that essentially operates with a flash that's a picosecond long, we're going to have to involve ultrafast lasers. So let me just explain briefly how those work. I don't know why I'm picking this up. It still doesn't work. Here's a concept, like an optical cavity in a laser. So it sounds complicated, but all you really need to know is the following. A cavity is essentially two mirrors separated by some distance. And between these mirrors, you can have what are called modes, essentially illustrated here as what we would call standing waves in a cavity. All the way from, you can have infinitely many of these. You could imagine that, keeping in mind this concept of interference, it's possible to have the right combination of these to produce, when you add them all together, you end up with something where essentially everywhere you have destructive interference, but only for a small amount of time do you have constructive interference. And so what this means is that it's possible to play around with the phase, which is to say literally the position of these waves in this direction, such that when you add them up, you get something like this. So this, in essence, is a technique which is called mode locking. And this is how you produce ultrashort laser pulses. So that was very cool when this was developed in the late 60s, early 70s. But the initial problem was that although we could produce really fast ultrashort laser pulses, they were so weak that you couldn't really use them effectively as tools. So recently, a Nobel Prize was awarded to actually someone I was fortunate enough to have teach me optics as an undergrad. So Donna Strickland in the top corner, along with her PhD supervisor, they got the Nobel Prize for essentially figuring out how to take these ultrashort pulses and really boost their energy a lot. Yeah, it's only fitting that I talk about this, not just because it won the Nobel Prize a few weeks ago, but it's literally the laser that I have to wrestle with every day. So it's very related to the work that I'm talking about now, and it's essentially the main tool in doing what we call ultra-fast experiments. So the idea behind taking a short laser pulse and then boosting its energy is the following. You kind of have to take one step back in order to take essentially 10 steps forward in this case. You have an input pulse, which is short, and you put it through some fancy optical components that are similar to the ones that are producing that diffraction pattern, but slightly different in technical ways. Consider them as fancy mirrors. So once you shine the light on these fancy mirrors, it's going to cause light that has a longer wavelength to travel a shorter path, and light that has a shorter wavelength to travel a longer path. And what this does in time is stretch out that pulse. Once the pulse is stretched out, you can give a lot more energy to it without without to quote these people, without blowing up your laser. Because if you tried to increase the energy of that laser pulse when it was really, really short, the matter that would be, that you'd be using in the laser would just melt. It would literally blow up. So you had to reduce the energy density by stretching out this pulse, give it a bunch of energy, and then recompress it. And essentially, after you amplify it, you put it through another pair of these fancy mirrors, and the reverse process, and then that amplifies the pulse. And this was huge, right? This really was a transformative invention where you increase the energy of the laser pulse by about a factor of 1,000,000, which won a Nobel Prize. I don't need to say anymore. There's a picture of one that on some days I love, on most days I hate. This is essentially a commercial chirp pulse amplified laser system, which you can buy from companies that sell them to you. And this is essentially the workhorse in the lab that I work in. Okay, so now that we have this ultrafast laser technology, it produces very short flashes for us. This accomplishes our constraint for time, or our requirement for time. We need to produce some sort of pulse which is extremely short, shorter than what would be the typical, motion, the typical time in which motion occurs in a material. We still have this distance consideration that we have to keep in mind. As some of you may know, light is only a very small sliver of what we call the electromagnetic spectrum. It occupies, in terms of wavelength, only a few hundred nanometers of this colossal scale, right? Which ranges from radio waves up to X-rays and even gamma rays. You can see here the wavelength in meters ranges by 15 orders of magnitude, right? This is truly a spectrum. So, as we saw earlier, if you want to see something, you need to use wavelengths smaller than the object. So for atoms that are separated by distances, over here, we can't use visible light. What can we use? Well, we could use X-rays. It's one option. Can't use gamma rays. We don't really know how to make them that well. Plus, it's pretty dangerous. So we could use X-rays, but is there an alternative? Well, in fact, there is, right? We can use electrons, which normally would not be on the electromagnetic spectrum because they're not light. They're not really electromagnetic waves, but they do have wave-like properties, provided you can get them moving fast enough. And this is really informed. This was informed to us by quantum mechanics. Essentially, it says everything is a wave, right? In the right regime. And electrons, if you get them moving quick enough, will have a wavelength. So if you have electrons, if you're able to accelerate them at about half the speed of light, they will have wave-like properties where the wavelength is on the order of 1 to 5 picometers, depending on specifically what velocity they're moving at. So this is exactly the length scale we need, right? This is below the length scale we need, which is good. When we recall that atoms are separated by, let's call it angstroms, which is 10 to 100 picometers. So where would they fall in the electromagnetic spectrum? Well, they're way at the one end. So great, we want the shortest wavelength possible. So we have that. And this fact, right, that electrons can be used to take images really gave rise to a field in and of itself, namely electron microscopy, which is really the gold standard for spatial resolution and high resolution imaging. And you can buy these things if you have a couple $1 million, and you can take awesome pictures. You can image biological materials, and hey, look, you can even see single atoms. Perfect. See the scale bar here is 2 nanometers. I'm able to resolve atoms. Amazing, right? The electron microscope is actually a Canadian invention, ranked 16th, just beating out the snowmobile, and well behind of poutine. And insulin's number 1, that's fair. But yeah, it's just kind of funny, right? Basketballs, 21, and, Blackberries, 18. So the electron microscope was a big accomplishment, invented a long time ago, actually, but it took a while to really perfect. It took a while to perfect our ability to use it to actually see things at its ultimate limit. Okay, so we can put a check mark. Behind beside our distance consideration. So now we want to do something. Let's recall like the demonstration, which is visible over there. So, and inspired by this, right? Atoms in a material are arranged in an ordered manner, just like those lines on the piece of glass over there are arranged in an ordered manner. So if waves of an appropriate wavelength go through them, I'm going to produce an interference pattern. And it turns out if you do this with electrons in a material, indeed you do produce an interference pattern. So this is not imaging, these are not atoms, these spots that you see here. They're regions of constructive interference which are established by the position of atoms. So it's kind of an alternative representation of space. Great. Okay. Have we forgotten anything about time? Well, actually, these electron microscopes produce a steady beam of electrons, right? Remember, we need pulses, recalling our strobe, right? We need to make an electron strobe light. I should have just said that from the beginning. That's what we need to do. We need to make an electron strobe light. So we need to produce ultrashort pulses of electrons. How do we do that? Well, we go back to our laser, right? And due to the fact that those who won the Nobel Prize were able to get so much power out of these laser pulses, you could do all kinds of physics, which is called nonlinear optical phenomena, which basically means like take one color and make like 2 other colors. That's basically what it means. You make other colors from one color. That's nonlinear optics. So we can do that using the output of our laser, pass that laser through material, take red light, make blue light, take blue light, make ultraviolet light. Once we have ultraviolet light, we can take advantage of something that Einstein told us in early 1900s, where if you shine light, where the energy of that light is sufficient, you shine it on a metal, you're going to emit electrons from that metal. They're just going to come out. So that's exactly what we do. We have an ultrashort pulse of ultraviolet light. We shine it on a piece of copper, and electrons come out. Great, but we need to get them moving fast, right? Remember from quantum mechanics, these electrons only have useful wave properties if they're moving fast enough. So we put them in a big electric field, and we get them going about half the speed of light. Once we have that, we fire it through a material, and we produce a similar picture, except this picture is a snapshot, which tells you what this material is doing over the duration of this electron pulse, which can be down to about 100 femtoseconds, so 10 to the minus 13 of a second. So that is our strobe light. It's an electron pulse. This is what the camera looks like just down the hill in the chemistry building. It's pretty messy, but that's normal. Essentially, you have an optical table where the laser is. You produce the ultraviolet light somewhere on the table. You send it into this accelerator beam line. It hits a piece of copper. Electrons come flying out, go firing down this tube, and go through a sample, which is located about here. And then the image is collected after over here. Excuse me. So we pretty much have everything we need, right? And I have 10 minutes left, which is perfect. So now I'm gonna talk to you about what's called a pump probe experiment, where we essentially need to find a way to make a stopwatch, right? We need something that will start the clock, some reference for like when's the beginning of the events I want to take pictures of. And that's going to be just another similar laser pulse from our setup. So we're going to have our crystal material that we want to take pictures of. at some point in time, we're gonna hit it with a laser pulse, and then the atoms are gonna go crazy. We want to make a movie of that, and then we control the amount of time after which our electron pulse arrives and takes a snapshot, which is each one of these interference diffraction patterns. The point is, the time between this laser pulse and the time between this electron pulse is something we can control. And by varying that, we can reconstruct the evolution of a material as it changes due to that laser pump pulse. So just to summarize, laser pulse comes in, hits the material. After some time later, electron pulse comes, takes a picture. Keeping that at hand. Here are some of the things that we're capable of measuring. So we have a material, graphite, just like, hockey stick material or whatever. And we want to make diffraction patterns from that. So in response to the laser, what we're able to observe in these pictures are these peaks changing, right? Essentially, they get modulated as atoms move. And that can be seen here in the intensity, essentially the brightness of these peaks. They go up and down after the laser pulse, and that's kind of shown here. So before the laser pulse arrives, nothing's happening. Then once it arrives, they go down, and you see some oscillations. And what this corresponds to are atoms moving in the material with specific what are called phonon modes. So these are ways in which the material likes to move. So, and we can actually see this in real time. Another thing that happens after you excite the material is it actually expands. So here you can take the data and figure out the distance between sheets of atoms. How is that changing? And you can see initially when the laser pulse arrives, it increases pretty quickly and then it kind of wiggles. So right, you can imagine planes of atoms that are separated, laser pulse arrives, and then they kind of do this. And that's something we can see exactly here. Goes up, oscillates a bit at a frequency that corresponds to something the atoms are expected to vibrate at. What's another material that's maybe interesting? So you can make crystals out of anything, right? Some things are easy, some things are not. Essentially, all you need are specific atoms or specific molecules to be arranged in an ordered way. Here's an example of a phase transition in an organic salt, which is for short this Otto TTF molecule, which is essentially these chains that are stacked. And at low temperature, adjacent chains are kind of like bent. But as you heat up, they all become flat. And the electron scattering pattern which is produced, it's a bunch of spots, right? I mean, it takes a while before you can look at these things and really know what they mean. But the point is, the difference between this and this, we can watch that happen in real time. So some spots go away, some spots remain, and some spots become brighter or less bright. So this is really looking at the organization of this organic salt. These are just a couple research examples in our group and others that are doing these types of experiments, just to give you a feel. Another example is you can look at the surface of materials. So here's an experiment where they look at the surface of silicon. And essentially what they observe happen is the atoms are arranged in a particular way in equilibrium, but once you hit them with a laser, they essentially shift around and go into a different state. And the pattern changes in qualitative ways. Pretty interesting, and really the scope of experiments is quite vast. Any material which you could prepare as a crystal, you can look at in this way. So this has all been with electrons, right? But if you recall from the electromagnetic spectrum, these experiments are also possible with X-rays. And there's a lot of people who are actually doing this, and those people generally have more money. So this is an X-ray free electron laser facility, one of a handful, a half dozen or so in the world. This one's at Stanford, and it's part of what's called SLAC. And these things are like really amazing, right? This is like a $2 billion Department of Energy project, and it's simply incredible. I mean, it's on the scale of something like the Large Hadron Collider, but it's built for a different purpose. So, and you can see it's a few kilometers long, so that's definitely different than how long our machine is down the hill. But it can do some things better, that's for sure. But it uses X-rays. So how do you actually generate X-rays? Well, it turns out you have to actually start with a pulsed electron beam. So basically, you start with the instrument that we have down the hill, and the instrument that I showed a few slides ago. So you produce a pulsed electron source in the exact same way that I described in this talk, but then you feed it into what's called a LINAC, or a linear accelerator, where essentially the electron just gets kicked many, many, many times by really strong electric fields, and eventually it gets up to like 99.995 the speed of light, like GeV energies, giga electron volt energies. And once it's moving really, really fast, it passes through like a really fancy magnetic structure, which is called an undulator, which literally makes the beam go like this. So it's moving this way, and then you just drag it around. And as you drag it around in this periodic way, as you decelerate and accelerate the electrons, you're just emitting X-rays in a way that basically makes a laser. So this is a laser for X-rays, where the gain medium for all the energy is an electron beam that you're literally wiggling at a crazy rate.
And they're coherent?
Yes.
The X-rays are coherent?
Yes. They have ways to like the raw output here is not coherent, but they have ways to isolate coherent segments of the beam later, because they just generate a colossal amount. Yeah. So this LCLS stands for LINAC coherent light source. So, but yes, I've heard they're coherent, and they would need to be suitably coherent for diffraction. So the ultimate goal for these experiments, the justification for building these facilities is that you're going to do something amazing. You're going to understand how something really important happens, right? So what a lot of people are interested in doing is looking at biological molecules similar to the one I showed earlier. And this is called protein crystallography. People want to see why protein folds, why DNA folds, why everything that's biological. People want to know the basic processes that occur with these molecules. Because even though they might move around slowly in nature, what dictates what they do is something that happens sort of on these femtosecond, picosecond timescales. There's a competition of processes where the fastest one dictates the outcome. And people want to know what that fastest one is. So this is an X-ray scattering pattern off of something. And like this, this distance in real space would be like, tens of meters, right? You produce this pattern over like tens of meters, there would be just terabytes of data streaming off the instrument, and you don't even know what to do with it. You can't even keep this data on a hard drive. Like it comes off and then it has to be processed, and you can't even keep it after that because it's just too big. So that's why people make these facilities, and really collecting these images, which look a bit obscure. It's like, what the heck is this? But really, all the information about how these things organize in materials, it's all in there. You just need to know how to extract it, and that's what people such as myself and many others work on. So with 20 seconds remaining, just to summarize, we've really combined the benefits of what we would call ultra-fast laser science. That gives us time resolution. That produces short pulses. And then we can do a variety of things with them. We can We can use them to serve as a very quick flash, a strobe light. We can use them to generate electrons. And essentially we use them to, we use them to generate electrons or X-rays. And once we have these, we can harness the wave properties to produce interference patterns that tell us very intimately what a material happens to be doing in the time domain. So I hope that was clear. It was really, really fun for me to do this, and I'll take any questions that any of you might have right now. So thanks a lot for your time. Yes.
You talked about the capturing the excitement of graphene surface. Do you have any experiments going on around here with graphene?
We have looked at graph, or we've actually tried. It's difficult for us to produce a graphene sample that we can put into our instrument for sort of technical reasons. Essentially, it's either we basically haven't invested the chemistry manpower to produce a single flake that can be sort of suspended in our beamline. And if you wanted to grow a single flake, it's difficult to grow that on the typical substrates we use. So these are really technical reasons. So we've tried, but others who have different focuses but similar instruments have looked at graphene. We haven't looked at it. Yes.
When you're imaging the atoms, how do you know that your beam isn't perturbing them because of the energy going in and you're seeing an artifact?
You mean like the electron beam?
Yes.
Yeah. So this can happen. So there are certain excitations which can happen in a material. Like there's a form of spectroscopy which is called electron energy loss spectroscopy, where certain transitions are possible, where your electron can be absorbed essentially from your beam, and it can go into the excitation of really what's a high energy atomic excitation can occur. But this actually only happens in the electron volt range, and maybe 1 to 100 electron volt range. We are about 1,000 times higher in energy. So essentially, the probability of any of those interactions happening is extremely low. The kinetic energy of our beam doesn't excite any transitions at that energy, but it does happen at lower energies. Yes?
Why does Marty have this picture of the tennis player linked to the pump probe?
Yeah, so the pump probe method is really about taking snapshots so here's the tennis player. So the idea with this is that you have a very slow camera, like a slow sensor, but you have a fast flash. That's the idea. And so each time what you're taking a picture of is illuminated, only that gets recorded by the sensor. So what you see here is the evolution, right? In a pump probe experiment, it's really the exact same thing, except what you do is instead of having a continuously firing strobe, you have one strobe where you take a bunch of pictures of at that time, and then you move the flash to a slightly different time. You take a bunch more pictures. So essentially, I have to kind of draw this out. So let's say, you have a sample. Let's call it S, and then you have. So this is, okay, let me just draw. So this is time, and let's call it just for argument's sake, every second you have a laser pulse which goes through your sample. So this is the pump every second. Your sample has some actual behavior that occurs in response to this pump. So once the sample gets hit by the laser pulse, let's just call this sample temperature, just for argument's sake. that increases, and then it relaxes again. And before the next laser pulse arrives, the sample is back where it started. And so that happens again and again and again. And the question is, so the probe, the question is, where along these curves do you want to take a picture? And so if you put, depending on where you position your probe pulse, you'll sample some segment of this evolution, and you move that around to reconstruct everything, like you see here in one shot. Does that kind of make sense? Okay.
Can you repeat the name of the two Nobel Prize?
So Donna Strickland was a PhD student who I guess that was her project, and her supervisor was quite a famous physicist named Gérard Mourou, who was at Rochester at the time that this work was done, but now he's at École Polytechnique in France. Yeah. Yes.
How does the so-called amplifier actually produce the signal?
The laser amplifier.
Yeah, laser amplifier.
Yeah. So I didn't really have time to get into this in detail, but what makes a laser? So light amplification by stimulated emission of radiation. So what this involves is a slab of material that people call the gain medium. So essentially what this is a slab of material where if you shine light of one color, you cause an atomic transition, which when that relaxes, emits light of a different color. So you get some absorption, and then there's a relaxation, and then what gets emitted is what the lasing light actually is. So, and this emission process is what people call coherent. Basically, you can generate more and more photons out of that, and you basically have this thing going in an amplifier, and then when you put the ultrafast laser pulse through this gain medium, it essentially inherits that energy, and you essentially bounce it back and forth through that gain medium until it gets what we would call saturated, or until it's basically acquired as much energy as possible. So think of it, there's like a source of energy, which is produced by what we would call a conventional laser, just conventional lasing. And then you put an ultrafast laser pulse through, which is light, which is of the same type of light that the lasing is happening, and it just takes energy from that medium. So that's kind of how it works. Without getting into, there are a lot of little technical details, and rigorously what I'm saying is probably not totally true, but more or less that's what happens. Yes.
That explanation touches on a confusion I've had throughout the lecture. You've imaged this process of lasing and then diffracting the laser output as if there were multiple wavelengths in that initial laser pulse. And that contradicts what I understood about lasers, that they're monochromatic. Are you actually dealing with monochrome signals, or are you making multiple signals of all these vast different numbers of wavelengths?
So I guess there's a few things to unpack there. I would say if something is truly monochromatic, it's what we would call a CW signal. So it is a wave, but it's continuous, right?
Yeah.
By virtue of
Fourier transform?
Exactly, by virtue of the Fourier transform, which is something I didn't want to get into here, but it's what it is. If you want to make a pulse, you have to introduce other frequency components. So you're absolutely right in that the pulse is not monochromatic. It does have a central wavelength, but there is also a bandwidth to that.
Okay, that explains the confusion.
So that's what's happening. Yes. So I tried to get through this talk without having to like go down that rabbit hole, because I would have been on slide 2 at that point. But
Okay,
but yeah, that's essentially the idea.
and
Yeah.
the same goes where all of these signals where you are
Yeah.
chirping, you have the Fourier transform of a pulse.
Yes, absolutely. And so there are some regimes where that will limit the type of resolution you have, like because you have multiple wavelengths in principle, but this is a trade-off that we're willing to deal with to have time resolution. We need to make the pulse, basically. We need to make it short, and if we're introducing other frequency components, most of those consequences we don't have to deal with. But yes, they are real, for sure.
And then the final question, in this thing where you described the probe, and you said the probe was slow, do you end up multiplying the...
In what I drew on the board?
Yeah, you end up pumping it just like your gain median multiple times until you can sample it once with...
No, usually you, in this case, you're pumping it, but you're making sure that it returns to, by the time the next laser pulse comes, you want to make sure that the sample is back where it started. That if you don't do that, then this stroboscopic technique breaks down. At least the way it's implemented in a pump probe technique, and you have to do some other tricks. Yes.
How does this compare, like what you're doing and what you're measuring, the motion? How does this compare to LIGO? Because they're measuring something, a distance that's really, to my mind, smaller, way smaller than
Yeah. So, must admit, I don't know all the details about LIGO, but essentially, that is and I guess that was discussed. I don't know at the last Physics Matters lecture. I don't know if you were here. Anyways, but essentially this infers wave-like properties from an interference event, where you've made the detector so extremely sensitive by essentially having the interference arms extremely long. So I would say that is a bit different in this case because it's aimed at detecting whether or not an event happened, right? Whether or not this wave, an interference pattern, which is suggestive or indicative of a wave, happened and therefore is attributable to gravitational waves. Whereas, it was more of a detector experiment, right? So that's like, did this happen? For us, it's more like how it happens. Like we know something's going to happen, but we want to see how it happens. So I don't think I truly answered your question, but I would say it's very different. So it's very different type of experiment. Yes.
When you started the lecture, you showed us that there was a lattice structure of the atoms in the material.
Yeah.
Then you present these imaging techniques. So what do you know now?
What do we know now about
After all the
materials?
pictures? Yeah.
Yeah. So great question. No, we at least tell people we know a lot. Essentially, tying it into what I articulated at the beginning, which is why do materials form the materials they do, right? It's not always obvious that if you have a bunch of atoms that what makes them form this solid versus that solid. Why do they order in this way versus the other? And what that's rooted in is what we would call the fundamental coupling mechanisms between various interactions in a material. So we know that electrons can interact in materials, and we know that the position of atoms, there are excitations that occur in the form of these oscillations. Right now, these are called phonons. So phonons are waves in the atomic in the lattice. So the atomic positions will oscillate, but around the atoms there are electrons as well, right? So what happens in an ultrafast experiment is that the light pulse will really instantaneously excite the electron system. But what we then observe is how does that energy, which in the electron system, how does it transfer to the crystal structure? Because we've kicked it out of equilibrium, and we want to know how it returns, right? And with what rate does it return? And if we examine that rate, it tells us the strength of the coupling between atoms and electrons. I mean, crudely speaking, you heat up the electrons, they have a temperature, which is now hotter than the lattice. These two systems are out of equilibrium, and they'll need to reestablish equilibrium somehow. In some materials, this happens extremely fast. In some, it's a bit slower. And in some, it happens in a way which results in specific vibrations being populated or being excited before others. So this relates to what we call the electron-phonon coupling. And this is a central parameter in many different exotic types of materials. So it's kind of the core feature in why superconductivity occurs. And it's just a number which is not attainable by equilibrium methods. So that's one example, I would say. If you want to talk later about more, like, we can. That's kind of one, I would say. How are we doing for time? Like 30 seconds?
I think
We're good.
Well, I guess I will ask you to applaud our speaker once again. Thank you very much.